6 will have to be interchanged in order to satisfy this condition. So there is 3 and there's 6. We're going to put 6 here, put 3 there, which corresponds to this exchange. And then we go to 2, position 2 in 4 and 5. So we compare these 2 with 4 and 5, which is the values 2 and 4 and 5. So the larger one of those two is 5. And so we exchange 5 and 2. And so that would correspond to this exchange. And then finally we go to the first element. Now, in this case, it's a little bit more complicated. We are going to look at 1, which is position 1, and compare it with positions 2 and 3, which is 6. So there goes 6, and we put 1 here. We exchange those. And now, of course, the issue here is that the position 3 has to dominate the position 6, which it does not, because 1 is smaller than 3. And so we have to do another exchange. So the result of that is that we now have a heap which is 6, 2, 3, 5, 6, 5, 3, 4, 2, 1. So the last change was, of course, that we did the 6 and the 1, and then we had to exchange those in terms of what we did here. And so that then gives us the heap 6, 5, 3, 4, 2, 1. That is the heap that we would obtain from the original array 1, 2, 3, 4, 5, 6. And you can obviously verify that this indeed is a heap. And so that is the construction, and now we have to analyze what is the time complexity. Well, if you look at this, then you can easily see, if you look at the entire array, the second half requires nothing. No flips, because there's nothing to be verified. This condition is clearly satisfied. And then for the next half of that remaining half, so that first half, we cut that in half, and so the second portion of that will have at most 1 flip. So there's plus 1 times n over 4. This is a quarter of the entire array. And then, so that would basically then correspond to from the bottom, the second row. The bottom is, of course, the first row where we don't have to do anything. Then the one above, which is n over 4 in general, we have to do at most 1 flip. And then for the remaining quarter that we have now here, the second half is 2 flips at most. So that would be this. We had that case, 6 and 1 and 1 and 3. So there were 2 flips, but this is n over 8. And then for the remainder, there is 3. This goes in here and there and there. So there may be 3 flips, but this is n over 16. And then we go on 4 flips, n over 32, and so on. And in the worst case, if you look at that entire tree, well, it's a binary tree that is complete, except for perhaps a few things missing in the last row. And so that means that essentially we know what the height of the tree is. It's log base 2 of n. So this is log plus log base 2 of n. And we have only one element, which is the root. And so if we add this up, then this is basically n. This is nothing. This is a quarter. This is another quarter, so this is 1/2. And the remaining is less than 1/2 of n. So altogether, we need at most n flips, fewer than n flips, which, since each flip is order of 1, we're now talking about requiring order of n time for the purpose of constructing a heap. So even though it looks somewhat complicated to do, it actually is a quite efficient way of getting a heap out of an arbitrary array. And it is clear that regardless of what is in the array, the amount of time that is necessary to carry this out is no more than order of n. And so then we are going to look at what is it that we can do once we have the heap. So we've basically seen that getting a heap is order of n. Now the next step is how to get from a heap to sorted array. And in order to carry that out, let me go through the exercise that I sent you. This is a little bigger. It has 8 elements. 1, 2, 3, 4, 5, 6, 7, 8. So these are the positions. And we have 16, 10, 14, 8, 2, 12, 6, 4. This is a heap. You can verify that. Probably not a bad idea. 1 with 2 and 3, 16 dominates 10 and 14. 2 with 4 and 5, 10 dominates 8 and 2. 3 with 6 and 7, 14 dominates 12 and 6. And 4 basically just deals with 8, so that's 8 and 4. So this is indeed a heap. Now, we've already said that the fundamental property of a heap is that the first element is the largest element. And so what do we know about this first element? Where should it be if we wanted to have a sorted array?
At the end?
At the end, absolutely correct. So what we're going to do is we'll basically ruthlessly put it there. Now we're displacing that 4, so that 4 goes in its place. And now we have to do exactly the same thing that we did before when we had an element that we had to bubble in there into that, because now we want to get a heap again. Now, of course, the trick is, and that's the crucial observation, we are no longer interested in a heap involving the elements 1, 2, 3, 4, 5, 6, 7, 8. We are only interested in a heap involving the elements 1, 2, 3, 4, 5, 6, 7. Because we know already that in the 8th position, we have the element that we want to have there. And so what we're going to do is we're going to take the elements 1 through 7 and put that 4 that we got by interchanging the first and the last position of the heap we're dealing with, putting that 4 into that array so that what results is a heap, which means 1 is going to be compared with 2 and 3. So there is 14, and there is 4. And then we have 3 with 6 and 7. So there is 12 and 6, so we have 12. This is 14. And there's 12, and there is 4. So then now the heap that we have is 1. 14, 2, 12, 8, 2, 4, 6. We're only going up to position 7. Okay, because this is already where it's supposed to be. And now what we have here is a heap in positions 1 through 7, which of course, again, as before, has the largest element in position 1. And once again, we know where that element is supposed to go. It's supposed to go into the last position of the heap, which is 14, which is position 7. So there goes 14. And now we're going to look at the remaining elements, 1 through 6, and make a heap. So this was 6. So the 6 is going here. And so we have 6, 10, 12, 8, 2, 4, and we have to make a heap out of that. So 6 in position 1 has to be compared with positions 2 and 3. Well, 2 and 3 is 10 and 12. The larger of those two is 12, so 12 goes here, 6 goes here. Then we have 3 is 6, and that's the only one that we have to deal with, because 7 is already out of commission, because the heap that we're looking at is only 1 through 6, and 6, which is in position 3, dominates 4, which is in position 6, and therefore this is fine. So we now have the heap 12, 10, 6, 8, 2, 4. And now again, 12 is in the first position. It is the largest element, and therefore it goes here. And now we're looking at the heap. We're trying to construct a heap that consists of the first 5 elements. So we have 4, because we put the 12 in its place. So 4 and 12 are interchanged, so 4 goes here. Then positions 1 compared with 2 and 3, so this is 10 and 6. So there goes 10, there goes 4. Okay, and then we have 2 with 4 and 5, so there's 8. This is 4 and this is 8. So now we have the heap 10, 8, 6, 4, 2. And once again, the largest element is in position 1, which is 10. And so we know it's supposed to go into position 5. So there it goes. So 2 and 10 are interchanged, flipped, and so we now have 2 in position 1 compared with positions 2 and 3, which is 8 and 6, so we're going to do 8 and 2. And then we have 2 with 4. We are now only going to do the first 4. So we have 2 and 4, and 4 is occupied by 4, 2 is occupied by 2, so we're going to interchange those. So we now have a heap 8, 4, 6, 2. And once again, now we know where 8, the largest of those 4 elements, 8, 4, 6, 2 goes. So we go here. And so now we have 3. 2, 4, 6. 2 in position 1 is compared with positions 2 and 3. Well, that is 6. And then we have 2 is in position 3, so there's nothing to be done. And then we replace 6 and 2. We flip 6 and 2. And then we change 2 and 4. And so we now have 6 And finally, we're going to do the flip again, so 2, 4, and then 6, 8, 10, 12, 14, and 16. So this should go down there. And that means now we actually have the sorted array 16, 14, 12, 10, 8, 6, 4, and 2 in the places in which they have to be. So that then allows us to deal with the construction from the heap to the sorted array. Now, we've already said that the construction of the heap can in fact be done in time order of n. The sorted array, well, obviously what we have here is an algorithm that sorts by comparisons. And so if we recall that some time ago we demonstrated that every sorting algorithm that sorts by comparisons necessarily has to use order of n log n comparisons, and given that heap sort strictly uses comparisons, it follows quite clearly that since obviously order of n log n is the best one can do, that conversion from heap to a sorted array must take n log n time. Because if it were less than that, then the sum of constructing a heap and going from the heap to the sorted array would be less than n log n, and that would clearly contradict the result that we obtained, namely that it takes n log n comparisons to sort by comparison. But we can also show that directly because effectively, if you look at that tree, let's just pretend it's a complete binary tree, but there may be a few things missing here, but that's not really that important. What is important here is that we now always insert at the very beginning. That element that we displace is going to be stuck in at the beginning, which means effectively we start at the root, and now we have to continue going all the way down until we get a heap. And that means that in the worst case, we need a number of flips that have to be carried out that is proportional to the length of that path, which is, of course, the height of the tree, which is, of course, log base 2 of n. That's the height of the tree. And since we have n elements that have to be put into their appropriate place, it really follows that we need n times log base 2 of n such flips. And in that way, it follows directly that the number of flips, and therefore the time complexity of going from a heap to a sorted array, is in fact n log n, which is perhaps a little surprising, because you might think that the construction of the heap seems to be more complicated than the construction of a sorted array given a heap. But when it comes to the time complexity of the construction of a sorted array given a heap is actually longer, requires more time than the construction of a heap. The heap, of course, is, as I said, it doesn't really have that much information. The only thing that is clearly required and implied by the heap condition is that the first element of the heap, or the root of the tree, is exactly the largest element of all the elements in the heap. And that, of course, is what we exploit when we go from the heap to sorted array, because that tells us what do we put into the last position of that heap, and then we take it out of commission and do the elements with one array element less and convert them into a heap by sticking that element at the beginning. But that element is stuck in at the beginning, so this will always start from the root of that tree, if you want to think in terms of the tree, and that means the number of flips that you may have to carry out is proportional to the height of the tree, which is log n. And so that then gives you heap sort. It is clear that the time complexity is n log n. What about the space complexity? Well, what do you need? You need very little. You need a few things that run this. So you have the construction of the heap. Well, that means you go backwards from the there we are. You go backwards, you take the half of them where you don't have to do anything, and the next half of the half you have to do at most one flip, and then for the next half of that remainder you have to have at most two, and then for the half of that remainder 3 and 4. So that is basically then a loop that starts at the end and progresses towards the beginning, and for one of those insertions to put an element into something that was a heap but now is no longer, and to convert it then into a heap, you basically have to do a comparison. You have to do that comparison, AI to AI 2i and a 2i plus 1. So that requires one auxiliary variable, and so altogether it follows that really with a grand total of about 4 or 5 simple variables you can do the entire heap sort. So that gives you order of 1 space, which is of course very attractive because it doesn't require any more than minimum anyway. So whether you have 3 or 4 or 5 variables, they're all simple variables, so this is all order of 1, and that means heap sort is very, very economical when it comes to the use of space. It also has other advantages. Of course, we've already verified that it is n log n in the worst case. In fact, the worst case is probably when you start with an already sorted array, because obviously the whole idea of the heap is somewhat antithetical to ascendingly ordered arrays, because the first element is always going to be the largest element, and in the sorted array the first element should be the smallest element. So from that point of view, it is not very difficult to see that if you start with an already sorted array, this is just about the worst starting point for heap sort that you can think of. But even in that case, it is of course clearly n log n, and the number of operations that are necessary, even in the worst case, are not very many. You have the construction of the heap, which is n order of n, and it doesn't really require that much. This notion of flipping things into place, one flip is about 2 or 3 operations. And then you have the same thing here. So the constant that you carry along in that order of n log n time complexity is a small constant. It is something like 3. It is larger than merge sort. Merge sort has less than 2, but it is certainly much more efficient than, say, quicksort, which in the worst case, of course, is n squared. So the whole idea that you can do that with a constant that is hidden in that order of notation, which is small, about 3 or so, is certainly very attractive, because heap sort allows you to sort with no additional space except for a couple of variables. It also has perhaps an attraction in that it is not recursive. I think you have probably figured out that when you had to come up with the worst and the best cases for quicksort, you had to think quite hard to get things organized so that you understood really how quicksort works, and that, of course, was directly related to the use of recursion. Well, heap sort doesn't require any recursion. Heap sort is a purely iterative algorithm, and so if it turns you on, you could program heap sort in a BASIC, in COBOL, in Fortran, all of which do not have recursive capabilities, and still you will probably get a very good sorting algorithm. So that is what I wanted to say about heap sort. Any questions about that? Well, there are two arguments. The first one is, of course, it has to be n log n. Because if it weren't n log n, then the lower bound that we derived would be wrong. That's sort of an indirect argument. The direct argument is that when you take, so let's take the first step. We interchanged the 16 and the 4. That basically meant our 16 was somewhere here. And there was a 4. The 4 is here. So we interchanged that 16 and the 4. And that meant that we put the 4 there. So the 16 is now here. The 4 is now there. And then we have to go down. And in each step, to go down to the next level, we may have to do a flip. In fact, we did have to do a flip. We had 4, and so we put the 4 there, and that was then compared with 10 and 14, and so the 14 was replaced by 4, and then we had 6, so that position 6 contained 12, and so we had to flip the 4 and the 12. Okay, and so that meant in this case we had to flip here once, we had to flip here twice, and then we had to flip here a third time. First flip was, of course, this, exchanging 4 and 16. The next one is 14 and 4, and the next one was 12 and 4. Okay, so that meant that in general, if we have n elements, then the height of the tree is log n, and for each of those elements on a path from the root to a leaf, we may have to do a flip, which is, of course, order of log n. And then we have n elements for which that could happen. that means that we have basically altogether a time complexity of n times log n. Does that make sense? Okay, any other questions? All right, then let's look at one other algorithm which seems to contradict many things. We'll look at that. This is what is known as radix sort or bucket sort. A bucket sort. So let's look at an example. Say I have ternary strings. We have 0, 1, 2. These are the three the digits that we're looking at. And let's say I have 0, 1, 0, 1, 1, 1, 1, 0, 0, 0, 0, 0, 2, 2, 0, 0, 2, 2, 2, 1, 2, 0, 2, 0, and 1, 2, 1. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's throw in one more. 2, 2, 2. Okay, so now the way in which this is going to be carried out is we have basically three buckets, one for each of those three digits, 0, 1, and 2. And we go through that list of 10 elements, and we first consider the last digit in each string. So that would be 0 or 1 or 0 and so on. And we put the string into the bucket that corresponds to that last digit. So we have 0, 1, 0 obviously goes here, and 1, 1, 1 goes here, and 1, 0, 0 goes here, and 0, 0 goes here, and 2, 2, 0 goes here, and 0, 2, 2 goes here, 0, 2, 2, and 2, 1, 2 goes here, and 0, 2, 0, 0, 2, 0, and 1, 2, 1, and 2, 2, 2. So that was according to the last digit. And now we repeat the whole exercise, taking the elements in the order. Quick question. Yes?
Does 2, 1, 1 go into the 1? Or why is it?
Sorry. You're right. 2, 1. What did I? 2. 2, 1, 1. Okay. All right. This. 2, 1, 2. Okay, 2, 1, 2. Yeah, I'm 2, 3, 4, 5, 6, 7, 8, 9, 10. What? I'm now confused. What did you ask?
There appeared to be a 2, 1, 1.
Oh, I'm sorry. I probably wrote 2, 1, 1, but it's really 2, 1, 2. Sorry about that. Sorry. Okay. Getting ahead of myself. So, but let's verify. This goes in 0, this goes in 1, this goes in 0, this goes in 0, this goes in 0, this goes in 2, this goes in 2, this goes in 0, this goes in 1, and this goes in 2. So this is all correct. And now we repeat the exercise, except now we're looking at the middle digit. We're taking the elements in the order in which they were put into those buckets. So the first element is 0, 1, 0, so that goes here because 1 is the middle digit. Then we have 1, 0, 0. 0 is the middle digit. 1, 0, 0. 0, 0, 0. 0 is the middle digit. 2, 2, 2, 0. 2.
I think you skipped 111.
No, I haven't skipped. No, I'm working through this in the order in which it was put in the bucket 0, followed by the elements that were put into bucket 1 in the order in which they were put in, followed by the elements in bucket 2 in the order in which they were put in. So I put 0, 1, 0, which goes here. 1, 0, 0, which goes here. 0, 0, 0, which goes here. 2, 2, 0, which goes here. And 0, 2, 0, which goes here. So that finishes all the elements in the bucket 0. And then I go to the next one. 1, 1, 1, which goes in here, and 1, 2, 1, which goes in here, and then finally 0, 2, 2 goes in here, and 2, 1, 2 goes in here, and 2, 2, 2 goes in here. Everybody clear? And then finally I'm going to do the thing again, the same exercise again, except now I'm going to go for the first digit. And so I have, again, my 3 buckets, 1, 0, 1, 2. And so, again, I go through the elements in each bucket from 0 to 1 to 2 in the order in which they were put in. So I have 1, 0, 0, which goes in here. And 0, 0, 0, which goes in here. And 0, 1, 0, which goes in here. And 1, 1, 1 goes in here. 2, 1, 2 goes in here. 2, 2, 2, 2, 2, 0, 0, 2, 0, 1, 2, 1, 0, 2, 2, and 2, 2, 2. And if I now look at the elements, again in the order in which I put them into the 3 buckets, 0, 0, 0, followed by 0, 1, 0, 0, 2, 0, 0, 2, 2, 1, 0, 0, 1, 1, 1, 1, 2, 1, 2, 1, 2, 2, 2, 0, and 2, 2, 2. What do I have? Nobody? 0, 0, 0, followed by 0, 1, 0, followed by 0, 2, 0, followed by 0, 2, 2.
It's sorted in numerical order?
It is sorted. So now this is sort of a little bit of magic, isn't it? Because obviously I didn't do any comparisons. I didn't do anything. And if I have m elements, m digits in each string, and I have altogether n elements, then I have m times n time complexity. And if m is constant, then I have order of n, which of course is a little bit worrisome because we've made the argument that sorting by comparisons requires n log n. Now, there are 2 arguments. One is sort of a legalistic argument. There are no comparisons, and therefore the argument that we need n log n comparisons to sort by comparisons doesn't apply because we don't really have used any comparisons. After all we do is stick things into buckets, and that is it. Now, that's sort of the legalistic argument. which obscures what really is happening. What really is happening is that if we look at the length of these strings, it does not really work to assume that they're of constant length. Because in order to represent n things, if we have b elements, in this case we have 0, 1, and 2, so b would be 3, we need log base b of n length of the strings minimally in order to represent n things. This is if b is 2, if these were binary strings, then it would be log base 2 of n. And since log base b of n is order of log base 2 of n, we've talked about that a number of times, for any b greater than 1, it follows that this m really has to be order of log base 2 of n. And so effectively, this isn't order of n, this is order of n log n in time. And so we really don't have any violation of our lower bound for the number of comparisons, which really is a proxy for the time complexity, the number of operations that have to be carried out. Okay, any questions? B in this case is 3. We have 0, 1, and 2. These were the 3 elements, 3 digits, if you will. If B were 2, you would be dealing with binary strings. I didn't want to do binary strings because binary strings get abused all the time, so I decided to go with ternary strings. So in this case, B would be 3, but if you take just binary strings, then B is 2. And so obviously, if you have 16 bits, then there is no more than n. N basically would have to be less than or equal to n to the 2 to the 16, which doesn't really do much. Any other questions? Any questions about anything else?
Open to doing these lectures through other services, or do you like Skype?
I basically use whatever is, the department set this up for me, and if you want to know what I like to be in front of a live audience and lecture.
Are you open to trying something else that's easier?
Probably not. I mean, I had a hard enough time learning Skype. Why?
Would you like to learn something easier? Microsoft Teams seems to work a lot easier. Anybody else agree?
Yeah.
Well, it is cumbersome, but I looked at all the possibilities, and given that I'm at home and can't be in the office, I decided that this was probably the easiest. It is a little cumbersome, and of course, as you have already seen, there are several points of failure, but I intend to struggle through, and I hope you come along with me.
I had a question on Theory 3 on the homework.
Yes.
So I've been working on it, and from what it seems, I've got two approaches so far. I worked out a formula for the total possible number of parenthesizations, but I'm not sure whether I should use that formula and use that as a divisor for the total number of total amount of work we would do for
Well,
any.
no. I think you're overthinking this. What really happens is that what you, if you look at the construction for the maximum or the I'm sorry, for the optimal number of scalar multiplications, there is this k, right? You have to try out. Now that k is basically the number of possible parenthesizations at that point, because it basically, the k says what is the last multiplication that I'm carrying out. Now, when you look at the SIK in that formula, the SK plus 1 J, well, each of those S's then comes with its own number of possible parenthesizations.
Yeah.
And so all you have to do is store that in the S and use it in order to compute the average.
I'm sorry, could you repeat what you just said? Just the last sentence.
You store that number of parenthesizations that corresponds to a particular SIK or SK plus 1J, and you use that then in order to calculate the average of whatever else you have, because now you're looking basically at the last level of the parenthesization, the last multiplication. Okay, and that last multiplication then corresponds to a number of k's that you have. Mm-hmm. And now each of those, the SIK and the SK plus 1J, also correspond to a number of possible multiplications. They don't necessarily have to be the same, because they could be in different places in the array S. But that tells you, if you store that number, how many possible parenthesizations there are, then of course that will give you the average, and you can then use that. You don't really have to derive a formula.
Okay.
All right.
I'll pick on that one for a while.
Okay. The assignment, as I told the other class, is going to be due by 6 p.m. on Wednesday. Any other questions? Well, if there are no other questions, then I will, with luck, talk to you on Wednesday again. Bye-bye.